And then we have the set of events, which are labels on the transitions. So you have an A, B, and a C event. And the set of states for this specific example is Q1, Q2, Q3, Q4, and the set of events is A, B, and C. Then we have a transition function generating the transition between the states, and that is a function in this case with the arguments of the states and events, and that gives you a mapping to a new state.
Keep a track and record.
Sorry?
I'm sorry.
I can continue, or?
Yes, please. By mistake, my mic was on. I'm extremely sorry for that.
Okay, so no problem. So in this case, we have one transition from the initial state Q1 via the event A to the state Q2. So this is one example of a transition from Q1 to Q2. And then you have from Q2 to Q3 and from Q3 to Q4 via the event C. So these are the three transition or mappings from the different states here. Note that this function is actually what we call a partial function because it's not defined for all combinations of states and events. For instance, a transition from Q2 via the event A is not defined because from state Q2 there is no possibility to take the event A. So it's in that respect a partial function. If you would like to get a total function, which is quite common in the literature that it's defined by a total function, then you have to introduce self loops on the events that don't generate any transition to other states. So for instance, you could have a self loop here in state Q2, including A and C. So the events A and C means that you just stay in Q2. And say in the last state here, you would then have a self loop including all three events A, B, and C, because you can never, this is a terminal state, so you will stay there forever. Okay. And generally, I use the notation here that the next state, what I call the target state, is denoted by Q prime, and that is a function of the source state where you are right now. So, for instance, from Q3 to Q4, if Q3 is the source state, then called Q, then Q prime is the target state Q4 in this case. As an alternative to a transition function, you can also introduce a transition relation, which is a bit more general. And in that case, you have a tuple including three elements: the source state, the event, and the target state. So that's an element in the relation including Q cross sigma cross Q. And this is a common way to define what we call non-deterministic automata. This is an example of a non-deterministic automata where you have the same event going to two different states from the initial state Q1. So from Q1, when A happens, you don't know if you go to Q2 or you go to Q3. Both can happen. And that is a natural way to model, for instance, human interaction, where you don't know if the which kind of event the user, by clicking an event, the user can mean different things, and you could come into different states depending on the specific choice that the user takes. But if you are not sure which specific action the user will take. You just say that, okay, the user will push some buttons and you will arrive either to Q2 or Q3. Then you can model this in this non-deterministic way. Also note that in this case, we have two initial states, Q1 and Q3. So that means that initial state is a set, while in the basic definition, I assume that I only have one specific initial state. And if you have only one initial state and you only have, so to say, one unique mapping from each state for a given event, then you get a deterministic system. Alternatively, a non-deterministic system can also be defined by a transition function where the output is not a specific state, but a set of states. And there we had use of this power set. So for this way, for instance, in this case, when we have from Q1, you can get either to Q2 or Q3. You can define that by a transition function where the result of that mapping is both Q2 and Q3. That is an example of a transition function where the result is a subset of all possible sets in Q. So these different choices are possible. So specifically for non-deterministic systems, either you have this extended transition function or you define it as a relation. So now I give you a few examples of automata, including some specific properties. The first one we have already seen here. The second one includes an alternative. Either A or B brings you to state Q2, and that can also be just written as A and B on the second line, or A comma B, I would say, is maybe more common. So A comma
Bengt,
yeah.
There are two people who are saying that the slides are not changing. Have you changed the slide? You're still
yes. So I stop and start again.
Yeah, sure. And can you make it full slideshow so that?
Yeah.
Yes, now we can see that. Thank you.
Can you see a slide here with automata examples?
Yes.
Yeah. So alternatively to this alternative transitions, Q1 with an A or an B to state Q2, you can also write that as A comma B or AB, meaning that both possibilities are bring you to state Q2. Sometimes also a notion is used calling the active events, and for each specific state we ask which events are possible, and in this state Q1, A and B are the possible events, and that is then called the active set of event. In case D here we have two loops. First one with only the B loop here in state 3. So you can stay here and go on, but we assume normally here that it's still a finite set of events that should be executed. So finally, you will make a C and bringing you back to state Q1, and then that can be repeated again. So it will be interesting to also generate what we call a formal language for this example. And that will come quite soon. Yes, it comes here about formal languages. So then first we need to define what we mean by a string or a word, which is another synonymous word, word actually, or notion for these strings. So an automata generates, in this case, in our example, first the empty string. That means that you're still in the initial state. And then the string A, and then AB, and finally ABC. And those are the only strings that can be generated by the first automaton here. Epsilon, A, AB, ABC. The language for an automaton is then denoted by the set of strings that are generated by this automaton, and we call that then the language of the automaton, L of A. And in this example, it's then the set of strings epsilon, A, AB, ABC. So then we need to also introduce something we call the set of all strings for a given set of events. And in this case, the alphabet, the A is sigma is ABC. And then the set of all strings you can generate by ABC is then, or a general set of events, sigma, is called sigma star. And sigma star then generates all possible combinations of words based on these events ABC. So first, the epsilon word or epsilon string is a part of sigma star. Of course, the individual events A, B, and C, but also AA, AB, AC, BA, BB, BC, CA, CB, CC. And then we go up to 3 events in your string, and then the first one is AAA, AAB, AAC, etc. So think about all combinations that can be generated by this ABC. And actually, this continues for, I shouldn't say forever, because when we talk about sigma star, we still assume that it's not an infinite number of elements in your strings. It's still a finite number of elements in your string. But still, finite could mean that it's millions of elements in your string. And then it's interesting to note here that any language for an automaton is then a subset of this sigma star. And that's the reason why when we want to be formal, we talk about sigma star as the most flexible system we can think about. And then every automaton is a restriction of this sigma star, where you pick out only a subset of the strings in this sigma star set. Now I switch to a new page where I talk about continuation of formal languages. You can see that? Okay, no response?
Yes.
Yeah, thank you. I just ask sometimes to get confirmation that that it's not this problem which we have already realized here. So any string can now be considered as a concatenation of 3 substrings, namely a prefix of S, a substring of S, and a suffix of S. So in this case, our string S includes 3 parts here. I have divided into 3 parts. First T, followed by U, then followed by V. And then T is called a prefix, U is a general substring, and V is the suffix of S. So for instance, in the case of S being the string ABC, examples of prefixes are anything that starts from the beginning, so to say, of this. So epsilon is a prefix, A is a prefix, AB, and also ABC. But for instance, BC is not the prefix, it's rather a suffix, BC. So a suffix always includes the last element in the string, and prefix always include the first element in the string, plus epsilon in both cases. And the substrings are all simply all sub strings of this string ABC. Now you can also extend this transition function to also operate on strings, not only individual events. And then we make a recursive or an inductive definition of this. So we say that delta of q comma epsilon is still the same state. You have not moved at all. Then if you would like to define what is the transition from Q to a string S followed by sigma, it's actually the string you get from, or the state you get from delta of Q comma S followed by the event sigma. Note that this delta of Q comma S is a state going from the state Q via the string S to a new state. So to exemplify this, we can note that Q1 is delta of Q1 comma epsilon, while Q2 is delta of Q1A, which brings you to Q2, while Q3 can be expressed as first a transition from Q2 via the event B to Q3, but Q2 can also be described as the transition Q1 comma A, which means that is the string, Q2 is delta of Q1 comma A, sorry. And by this definition, this recursive definition, we can also say that this can be described then as S followed by sigma, in our case A followed by B. So in this case, it means also that Q4 can be represented as a transition from Q1 via the string A, B, C. So this is a quite useful extension of the transition function. Then we have operations on languages. And note that we had first some operations on strings, and now we talk about operations on languages. The first one is concatenation, and then we assume that the first language is a set of strings in sigma star. L1 is a subset of sigma star as well as L2. And then L1 followed concatenated by L2 means that it's all strings where S includes first a part from L1 and then followed by a part from L2. So S is S1 followed by S2, where S1 belongs to L1 and S2 belongs to L2. So this is the formal definition then of concatenation of languages. So in our example, a simple example here is that we say that L1 includes only the these are two strings. They are not events, they are two strings. So first a string S1 and T1, and in L2 a string S2 and T2. The concatenation of these two languages includes S1 followed by S2, and also S1 followed by T2, and T1 followed by S2, and T1 followed by T2, and all these you see here. So this is the concatenation of two languages. Then you have the clean closure, which actually clean was very much the inventor or the researcher that 60, 70 years ago formulated a lot of these formal language procedures, and including the star operator. So the star operator for a language means that L star is epsilon union with the language itself, but also the concatenation LL and also LLL, and going on like that. So this is the union of all concatenations L to the power of K, LK, from K equals 0 to capital N, where N is an arbitrary large but not infinite number of languages. So this is the clean closure. And for instance, the clean closure of the language, including only the string ABC, is then, of course, L star equal, yeah, then we denote that by ABC and a star on that string. But note that it can also be not on the language can include not only one string, but in this case it does. So it includes epsilon, ABC, 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 etc., with adding more ABC all the time. The prefix closure is all prefixes for a given string. So it's S, an element in sigma star, such that you take first such that there exists a string T in sigma star, and that ST is also a member of the language. So here you see that S can be considered as a prefix of the string ST, and ST is in the language L, and that does not mean that S is in the language L, but S is in the prefix closure L bar of the language L. So for instance, if L is the string ABC, then the prefix closure includes also all prefixes like epsilon, A, AB, and also ABC. Now I will just exemplify with one more example, and in the end here coming up with an interesting property which is defined based on formal languages, and that is related to what we call uncontrollable events. But let me come back to that. First, you could consider what I show you here just as some formal languages of any type. But now let's say that you have K equal AB and L equal AB and CD. So K is a subset of L in this case because it includes both only AB, while L includes also CD. Then we look at the prefix closure of L and K. K has epsilon A and AB, while L has epsilon A, AB, C, CD. Now we can say that if you have an automata S with these events, then the language for this automaton includes epsilon, A, and AB, and this automata has a language epsilon, A, AB, C, and CD. So that means that the language of this automaton is actually the prefix closure of L. Note that L only includes AB and CD, and K only includes AB, while the automaton for both S and A includes also the prefixes of this language, of these two languages. So L bar is the prefix or is the language of the automaton, while L only includes AB and CD once again. Then I ask the following: is K bar followed by something we call just formally now a set of events, in this case only one event B, intersected with L bar? Is that a subset of K bar? We can take this just as a language property, and I will explain a little bit later on why this is of interest. Now let's ask the question, is this true? Okay, then we remember that K bar was epsilon AAB, and that concatenated with the event B, it's this, and then you see that concatenation of these two gives you B, AB, and ABB, because you add B in the end of these strings here. Then you take the intersection of that with L bar, and L bar was epsilon, A, B, C, and CD. So then the question is, the intersection of this, is that a subset of K bar? Let's see. When you take the intersection of these two languages or these sets, then you can find that actually it's only the string AB that is included in both these sets. So that's the intersection element. And then since K bar was epsilon A, AB, we see that yes, this expression K bar sigma U intersect with L bar is actually a subset of K bar. On the other hand, if we extend this sigma U including, or take another version of A, C, and then you evaluate the same, epsilon AAB was K bar, followed by sigma U, AC, and that intersected with L bar. And if you go on and evaluate what is common here, what is the intersection here, you find that it includes only A and C. And then K bar includes A, but not C. So in this case, K bar is not, or let's say that K bar sigma U intersect with L bar is not the subset of K bar. Okay, so why I introduced this here is just to show you how you can, so to say, work with these set expressions and these language expressions. Now it happens that this expression here is a very famous expression because it expresses something called uncontrollability. And let me just to motivate this example, although we will discuss this later. But this sigma U, if that includes the event B only, that means that if the automaton want to execute B, then the supervisor in this case cannot refuse that. And you could also see that when you take the intersection between A and S here, then you see that in both of them you have this behavior A and B. And that means that the supervisor can follow what the automaton, or rather that the automaton and A and the supervisor S can work together in a correct way. On the other hand, if we say that this A is actually a plant which spontaneously can take either A or C, then we see here that, well, A, that is also part of the desired behavior given by the supervisor. So that's okay. But if the plant make a C, which I indicated here also as a possibility for an uncontrollable event, what I mean by an uncontrollable event is simply an event which the plant, or in this case A, decides independently of if the supervisor does like that or not. So A can spontaneously take a C. What happens then when you look at the combination of A and C? Then S cannot follow that because S cannot execute this C event. So that is an example of a situation where the synchronization or the coordination between the plant and the supervisor will not work. And this is a bad situation. So actually we must avoid this. But if this property is fulfilled, then the system is controllable and it was controllable for when sigma u was equal b, but not when sigma u was equal a comma c, because then c was not included in k bar, and that meant that you got a problematic situation here. We will come back to that, but this is just an illustration of why, or motivation why I'm working with these language operations, because we will use them when we also are reasoning about controllers or supervisors for systems. Now we come with something called regular languages. And then you could say that a regular language is have some restrictions compared to any arbitrary language. So far, we haven't made any restrictions at all, and that means that you could have language which are of more extensive behavior. But in our case, we will only consider regular languages. Why? Because the regular languages exactly are used to model automata. So that's why we restrict ourselves to a regular language. And you could say that if you have an expression in a regular language, you can always transform that to an automaton. And if you have an automaton, you can always transform that to a regular language. So that's why this is specifically important. And then a regular language is defined by 3 operators. The first is that we have this concatenation of strings. So you can, if you have 2 strings or a string S1 followed by a string S2, expressed as S2, you could in some sense consider this as a multiplication, but it's a hidden operator. So S1, S2, that's a concatenation operation. That can always be performed in a regular language. You can also take the union between 2 strings in the regular language. So if you have one string S1 and another string S2, if you combine those 2 and take the union, then you still have a regular language. Now, in regular language, there is a specific operator for this. So there we don't write union, we write plus instead. So S1 plus S2 is actually the operator for taking the union of 2 strings. And what this S1 plus S2 means is actually that you have 2 alternatives. So, for instance, in this case, you have either the alternative AB or CD. And you could say that the language here could be considered as the union of AB and CD. That brings you to the language. And this is a regular language because the union operator is a part of a regular language. And it's also a way to describe these 2 alternative choices in the automata. Finally, we have the closure of strings, which means that we are also able to represent loops. So S star means in this case epsilon, S, SS, SSS repeated, etc. And we'll soon see some interesting examples of loops when we use this closure of strings. I said that I had 3 operators, but you see here that I still have a 4th item. And there is a derived operator, you could say here, which we call S plus, which means that it does not include the epsilon operator. Otherwise, it's the same as S star. So S plus at least must include the string S and SS, etc. So the 4th operator is a derived operator since S star is equal to S plus. Okay, so this was a lot of small stuff, but now we come to some interesting applications here. And I hope you will see some more examples of this in the tutorial also this afternoon. So if we look at this automaton A again, as we have had as the running example, A, B, C, then what is the language of this automaton? Well, we can say it includes epsilon, A, AB, and ABC. That's what you have here. But you could also say that it's all prefixes of the string ABC. So you could say that this prefix operator is not a specific operator for regular languages, but it's an operator which is useful to simplify notations, but it's not necessary to define a regular language. For this automaton, we illustrate here that we have an alternative, A or B followed by C. So that can be generated as AC or BC as two strings, two alternative strings, and then we take all the prefixes of that. So that means that you have epsilon, A, B, and AC and BC. All those strings are actually generated by this prefix operator on this string A plus B followed by C. Now comes something more interesting, namely that we have also a loop here. So this automaton, what kind of language does it have? Well, you see that you can generate first an A, a B, then you can repeat B a couple of times. So this B looping around here could be expressed as B star, but it follows first by a B, and then you make a C, and then you are back in the initial state again, and you can repeat the same procedure. So that means that the formal language is A, B, B star, which means that it can be 0, B, or it can be 1 or 2 or 3 or 10 or 100, still only a finite number of Bs, before you take a C and go back to the initial state. But then you repeat that, and that means that I add one more star operator on the whole string expression I have here. And then you take all prefixes of this, and you get the complete language of this automaton. Now you see that B star can also be expressed as B plus. So the language of this automaton is actually A, B plus, C, and then a star operator on that, and all prefixes. Then we go on and talk about marked states and marked languages. And in that case, we introduce some specific, let's call them marked states or goal states or final states. Simply states which we want to be able to reach. So in this example, QM is the set of marked states, and all states are 0, 1, 2, and 3. So that's why we have QM 2, 3, and Q is the whole set. So that means that QM is always a subset of Q. The definition of this is just that you take the ordinary automaton, which we had before, and then you add a fifth element with the marked states, set of marked states. Now, it comes here an interesting remark that if you don't have any marked states at all, if your tuple does not include QM, then the assumption is that all states are actually marked. So if there is no specification of any specific marked state, then we say that QM is equal to Q. All states are marked. For this, we can now define also marked language. And The marked language is then all strings in the complete language such that there is a transition from the initial state via string S to a marked state. So delta of qi comma s is then a state, if that is a state that is marked, all such states in the language are included in the marked language. Then there is specific notion saying that a prefixed closed language is a language where the prefix closed language is the same as the ordinary language. And we can say that for any automaton, if you formulate the strings that generate the reachable states, then you have a prefixed closed language, because all prefixes are also included in the language. So that's a property of an automaton. While the marked language only include a subset of strings, namely those strings that brings you to the marked states. So in this case, the marked language only includes the strings AB and AC, while the complete language also includes epsilon and A. So that means that if you take the prefix closure of the marked language, you get the complete language of the automaton. But okay, this is not always the case, I will come to an example on that later on here. But first here we have an interesting example, which is not very advanced, but it's a little bit more challenging how to formulate the language of this system. First, we note that the marked states are the initial state, but also this state. Now we start by generating the marked language. And that includes first epsilon, you are in the initial state. Then you can generate A followed by B, and you get into another marked state. Or you can generate C followed by D and also bring you to this marked state. So AB plus CD is also part of, is also string, or we could say an expression. It's actually two strings, CD, AB and CD. But by this plus sign, this expresses a regular string, we can call it, or a regular expression representing these two alternatives. Now, this expression S, bringing you from the initial to that marked state, it can be followed by an E, and then you are back in the initial state. So then you have SE, and then you can take another S expression again, and another E, and continue like that. And by this structure, we see here that you can actually take a number of SE repeated, a number of SE, including the empty string. So here you have epsilon, SE, 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 and a third time, a fourth time, etc. That is generated by SE star, the clean closure of SE. But we also have this E event as a I see here. Okay, sorry. I see here that, for instance, if you assume that SE star is just epsilon for simplicity, then we see that, okay, we have epsilon as one element, but you also have S as an element. So epsilon or S, they are two elements in your marked language. So either you write S epsilon followed by SE star, or like here, you write first SE star, generating all loops, and then you also add the transition from this marked state, to this marked state. And this is the complete marked language. And then you take once again just to write a bar above, and you get the complete language. We can say that this is only possible fully if you have a prefixed closed language, or we can say if you don't have any so-called blocking states. Let me introduce another example where you can actually not use this operator to get the complete language, and that is the following. In this case, we say that the complete language is A, you can say A, B, and followed by B star, and all prefixes of that. That is the complete language for this A automaton, which can also be written as A, B plus, and all substrings or prefixes of that. But now, on the other hand, the marked language for this, the marked state is this state, and that means that it's only the event A one time that generates the marked language. So this is an example of a situation where if you take the intersection, the prefix closure of the marked language, you don't get the complete language. And this is an example of what we call a blocking system we want to avoid. So we don't want to have a situation where you, when you come to this state, we realize that you will never be able to get back to the marked state. From every state, we want to be able to get back to any marked state. So this is a non-desirable bad behavior, and we call this actually a blocking system. Okay, then we go on, and then I will define what I mean by a reachable state. You remember that we talked about that yesterday. And now I have a formal definition of the reachable states, and I also give you some examples and also relate this to languages, etc. So a reachable state is simply a state in the set of states, an element in the set of states Q, we call that small q, is reachable if there is a string in the language of L such that Q can be expressed as a transition from the initial state via the string S to this state Q. If this extended transition function exists from Qi to Q, then the state is reachable. There is a transition from the initial state to this state Q. And there is also an interesting property, namely that an automaton that only includes reachable states is called accessible. I wouldn't say that it's very important to use that notion, but it can be useful to have that notion. So if we look here at this example, then we can ask ourselves which states here are reachable. Obviously, state 8 and 9, they are not reachable because there is no transition from state 1 to these states. They are totally isolated. Also state 4. But more interesting is that also state 5 is not reachable because there is no string from the initial state to state 5. While there are strings from state 1 to state 2, 3, 6, and 7. So the set of reachable states are exactly then 1, 2, 3, 6, 7. And you could say that the language of that automaton is epsilon, A, C, AB, CD, but also AD. So this is the language of this automaton. So you could say that the language of an automaton generates in some sense all the reachable states. This means also that the accessible automaton only includes those reachable states. So it's this automaton, which is the accessible one. Now, the definition of a co-reachable state is that if there exists a string such that there is a transition from a state Q to a state in the set of marked states, then Q is a co-reachable state. So from any state, if it's possible to reach the marked state, then it's also possible to go from that marked state backward to this state Q. So you could say that another way to describe this is that co-reachable states are all states reachable from any marked state. So QC is the set of co-reachable states for an automaton A, and in our example, which are the co-reachable states? Well, you start in the marked state and you go backward, and then you see that all the states here except state 3 are backward reachable, and they are then called the co-reachable states. And now we include state 5 too, but not state 3. So 1, 2, 5, 6, and 7. This is called the co-accessible automaton then. And then there is another notion which is called the trim automaton, and that combines the reachable and the co-reachable states. And if you take the intersection between the reachable and co-reachable states in our example, we both skip that state 3, and we skip the non-reachable state. So we could say that by generating the trim automaton, first you skip all non-reachable states, like state 5, but you also avoid all blocking states from which it's not possible to go to a marked state. So this trim operator, or generating the trim automaton, is actually the generic procedure for generating what we call a non-blocking system, a non-blocking automaton, which is one of the very basic synthesis procedures of generating a control function for a system. Avoid all deadlock states and also states leading only to deadlock states. So by doing that and skipping all the non-reachable states, you get what we call the trim automaton. And this means that we come to the first synthesis of what we call a supervisor. You can also call it a controller, but the reason why we call it supervisor is that it acts more like a police, saying that the plant asks the supervisor, is it okay to do this or not? That's the interpretation or semantics of this supervisor. So now assume that we had this plant. Then if we generate the trim automaton, it's this automaton. And we have the specification that also state 7 is the marked state. Then it's interesting that if you take the plant synchronized with this supervisor, you get this closed loop system. You see here that I use the same state names in the supervisor as I do in the plant. 1, 6, 2, 7. And the events A, C, D, B. These 4 are the supervisor states. And if you then combine these two, you get the synchronous composition, and that includes then state 1 from the plant and state 1 from the supervisor. By event 2, by event A, brings you to state 2 in both the plant and the supervisor. And then by the event B, you get into the marked state, the state 7 in the supervisor. So from 2,2, you get into 2,7. And then I consider this as the marked state because it's marked in the supervisor. And since there are no specifically marked states in the plant, we assume that all of them are marked. And the rule is that a marked state should be in the synchronous composition, should be marked in both the plant and in both systems, both in P and S. And now it's marked here because all states in the plant are assumed to be marked. Okay, now time is 12. I think we could take at least 5 minutes break before I continue, and then I will go on for about 40 minutes. So let's see if we have some questions.
I have paused the recording. If you'd like to take a 5 minutes break and then questions, maybe?
Yeah, that's okay. Hmm?
Okay.
So now it works with the slide shift after the first problem there. Yeah, thank you.
So you have participants. If you have any questions, please feel free in asking. You can write on the chat box or you can unmute yourself.
Yeah. It's a bit of theoretical framework here, but not so much of
yes.
so to say applications around this so far. But at least there will come some more aspect. But okay, I mean, you could say that playing around with these automata is quite much of what this is about. Yes.
Yeah.
But you could say that this formal language is not. We could express it in this way: that if you look at the standard literature on this topic, there is a famous book by two persons, Cassandra's Lafatu, and they focus very much when they come to this part on language expressions for related to this synthesis and theory and so on. And why they do that is that because they have some ideas, or let's say that the theory was in the beginning developed specifically for formal languages. And it was made by a Professor Warnham from Toronto. And he liked this possibility to talk about, also not only regular language, but also, for instance, languages with infinite set of states and so on. So, but I consider that to be of limited interest. So for me, I prefer to have this automata description and try to formulate all things related to that. But if you go to the literature, you can definitely see that especially in the beginning and still now, most of the results are formulated based on these formal languages. But if you go to the AI literature on planning and so on, I would say it's more, definitely much more on automata. So it's in the line with that. I also go for automata. But to have at least 1 hour to go through the formal language, I think is reasonable. Okay, can a robot interacting with the environment be modeled in terms of a formal language, like, for example, in terms of synchronous composition or other automata theory concepts? Can a robot interact with the environment by model? Yeah, okay. Let me think a little bit about this. You could say that, well, if there is a behavior of a robot, which means that the robot, if you have started the robot to do something, you have started it, then you cannot, for instance, refuse the robot to make some own decisions. That could mean that without your possibility to influence, the robot will either go to left or right, say. If the robot has that option, then you could say that going to right or left is an uncontrollable situation with where, so to say, the robot has its own right to do what it likes. Interacting with the environment to be modeled in terms of formal language, like, for example, in terms of synchronous composition. Yeah, I mean, the synchronous composition comes quite much all the time here when we generate the closed loop. So as soon as you would like to construct a supervisor or a controller for, say, a robot or for something else, then you always use the synchronous composition to describe that. And then you could say that, well, some elements in the system that you want to control are uncontrollable. And actually, the most simple one is the sensor signal. I mean, you give a command and action to the plant, but the sensor is taken by the plant spontaneously. You cannot refuse the plant to generate a sensor event. That's the most natural way of thinking about uncontrollable things. It's something that happens by the plant. You cannot refuse that. That's the formal that's intuitive definition. But more so to say conceptually interesting is maybe this user interaction, where you could say that user can do a lot of things, and some of these things could be naturally described as uncontrollable from the supervisor point of view. But we'll come back to that. So now I think we go on. Any other questions?
Yeah, I have a query here, that what is this term formal in the formal language? I mean, what refers to this term?
Sorry?
Am I not audible, sir?
Yes, your
Can you
voice is
repeat?
very low.
So is this better now? Is this better now?
Yes, a little better, yeah.
So my query is that what this term formal is in this formal language.
Do you ask about the distance formal, or I don't understand?
You're still not very clear, Professor Goel. Can you speak a little aloud so that we can hear you properly?
So I
What
is writing?
What is this term?
Right.
Formal
what is the term formal in the formal languages?
Yeah. Yeah, that's a good question. The question is here about why do we call it formal language? Why don't just call it language? Well, I mean, you could say that it's quite formal in the sense that, I mean, normal languages, then we say that, okay, this is a word and we have some meaning of that. I mean, here we are just talking about language in terms of strings or words with just letters and so on. And what is the formal meaning of that? Well, yeah, I would say that it's just that it's more of a mathematical thing than an ordinary, so to say, spoken language. I think that's the reason why it has some formalism around. I mean, spoken language, we don't have a star operator on that. We don't have a concatenation operator on spoken language. If you don't, so to say, if you don't use these formal language operations to also define a spoken language, which of course you can do. I mean, of course, the concatenation between two words is obviously a sentence, and you can build two sentences, etc. So, but okay, I mean, there are a number of formal things around these operations on language, and that's the meaning. That's the reason why it's called formal.
So another term which is being frequently used is phrase structured. So is this phrase structured and formal is referring to one and the same thing, and obviously it is different from the natural language? Yeah,
you said something on. I missed the word you said in the beginning. The alternative to formal language was. Can you write on?
Is this better now? Am I audible? This time I don't know what happened.
Actually, your mic or this is creating
right,
a bit of issue.
Write your question. Write your question.
Okay.
What is phrase structure then? Yeah, I'm sorry, I haven't heard that. I'm not familiar with that at all. So I mean, I can just speculate. I mean, phrase is a part of a sentence. Phrase structured. Yeah, I'm sorry, I haven't heard that. So I cannot give any comment on that. Any other questions? Okay. Not anything more, then we will go on, and I will go back to my presentation. Let's see where we were. Yeah. We have now also some words about forbidden states. I mentioned that already yesterday, and if you remember, I mentioned that for instance, a state when two robots are in the same space, in the same area, could be considered as a forbidden state, as a specification to avoid collision between two robots. So the forbidden states are simply states that need to be avoided from a practical point of view. And for instance, a shared zone where only one robot can be at the same time is an example of that. So formally, I introduce then the notion, the set Qx as the set of forbidden states. And now if I introduce a specification saying that Qx equal state 6 is a forbidden state. So that means that now I have a specification where I consider Q and state 7 to be a marked state. I would like to reach that. And I would like to avoid state 6. And still, I also would like to avoid this blocking state. What is then the supervisor? Well, if you synchronize then P with this specification, you could say you generate a specification, and to avoid this state 6, you simply get this model. And that means that you take this route, this path A followed by B, and then you reach 7. This is the only good desired way to reach your marked state. You cannot anymore take this way, which was an alternative in this for this supervisor. Then you could take A, B, or C, D. But if you consider that 6 to be forbidden, then you have to skip that. So, okay, you could say that, well, isn't it enough that you take the supervisor and look at the forbidden states there? Well, the problem is that if you put some states to be forbidden, you could also generate new blocking states. So we need to make some additional evaluations to see that we still have a non-blocking system. Now we generate also the closed loop system, the plan synchronized with the supervisor, and we see that we get the supervisor, except that the names are different in the supervisor and the closed loop system. But you could say that these two automata, they have the same structure, but they have different state names. And formally, this is sometimes called that they are isomorphic. There is an isomorphic mapping between the states in the closed loop system and the supervisor. But maybe it's easy just to say, okay, you're free to have any names on your states, but they must have the same number of states, and you must have the same transitions between the states. So if you don't care about the state names, they are exactly equal. And then you are free to put any names of the states you like. If you have that situation, we still say that they are equal, but this equality is actually formally an isomorphic equality. And in some situations, you don't use that equal sign. You could also have some different markings for this isomorphic equality. But I use that equality also including this isomorphism. Now we also have the synchronous composition, which is very important. It's very crucial. And actually, I will introduce here something similar to the example I had yesterday, I see here now. But now we have the formal definition of this. Then we take two automata, A and B. And for the automata A, I use the superscript A on all elements here in the tuple. So this is a tuple, and the elements in the tuple are sets in most cases. Here, this delta is a function, but the rest of them are sets. In this case, the initial state is only one element. And then the corresponding B automaton has the same structure, except that we use the superscript B instead. How do we then define the synchronous composition between these two automata? As I said yesterday, we take the cross product between the two states, the two state sets. So the cross product between QA and QB. Generally, this means that we generate a lot of states which are not reachable. For instance, we can just take a look here and see, although this is a very small system, you have state 1, 1, 1, 2, 2, 1, and 2, 2 as all the combinations. So totally the cross product between the states 1, 1, 2 here and 1, 2 here, they include 4 states. So each of them have 2 states, and then together you get 4 states. While in the synchronous composition, in one case we only have 2 states, and in the other case we have 3 states, but never 4. So that means that the synchronous composition typically reduces the number of states or generate a couple of states that are not reachable. So that's why it's also useful to generate take the reachability analysis of this in this case to skip all the non-reachable states or to generate the trim automata. The event sets, there you take the union between the two. So the event set in asynchronous B includes all sets in A and all sets in B, or all events in A and in B, sorry. The transition function is a bit complicated, which comes later here, so I will wait with that. Then the initial state is the combination of the initial state in the first and in the second automata. So in our case here, we could say that the state 1 in A and the state 1 in B, they generate the initial state in the synchronous composition. While the marked states, there you could have more than one state in both A and B, and then you have to take the cross product also there. And then I remind you that if A does not happen to have any marked states, QM is not there, and maybe then also not QX, then you get actually QA cross QM B to generate the marked states, which is actually a typical situation in our applications where we have a plant without marked states and you have a specification with marked states. Then the forbidden states, there it's important that now it's enough that a state is forbidden in one of the automata to be forbidden in the synchronous composition. And that's quite natural. That, I mean, it's very serious if a state is forbidden, and it doesn't matter if it's an A or B. If it's forbidden in A, you can be everywhere. In B, still the total system is forbidden because you are in forbidden state in A. Or if you are in any state in A, but a forbidden state in B, you're also a forbidden state in the synchronous composition. So you have then to take the cross product between the forbidden states in A and all states in B, union with all states in A and the forbidden states in B. Simply, it's enough to be forbidden in either A or B. So then we have the delta function, the transition function. And now I use even here the cross product. So that means that these transition functions for individually A and B could also include some non-determinism. So for the same event, you could reach more than one state. But if there is only one target state for each event, then it's only that for a combined transition starting in state QA, QB, then you will run, if A is a shared event in both A and B, you will get into a combination of the target state of A and the target state of B. So in that case, if you have a unique state in both, you don't need to write the cross product, then it's just one element, delta A of QA A and comma QB, delta B of QB comma A. But if this is a set of states explicitly for the non-deterministic case, then you have to use the cross product. So once again, if you have a shared event, then you need to make a transition in both A and B. While if it's an event that is local only in A, then what should you do with B? Well, you stay where you are. You keep the current value, keep the current state in the second B automaton, while you make a transition in the first, in the A automaton. And the opposite, if it's a local event in B, you make a transition in B and you stay where you are in the first automaton. So this is the formal definition of the synchronous composition. And here we now have, okay, it's not exactly the same example as I gave you yesterday, but very similar. So we start in state 1 in A and state 1 in B, and that is this state which is also marked because it's marked in B, and in A you don't have any marked state, and that means that both of them are marked. So then this state is marked. Then you make a synchronous A, shared A, and you reach into the state 2, 2. Then you can make B and going back to the initial state again, because it's included in both A and B, and it's possible in state 2, 2. Now, if C is also an element of the alphabet of B, it means that it's a shared event. But since C can never happen in B, it can never happen in A either. So that is a trick to, so to say, forbid some transitions in the synchronous composition. And that means that the C event will not happen in the synchronous composition. On the other hand, if C is not a part of the alphabet of B, sigma B, then E is a local event in A. And then when you have reached the state 2, 2, it's possible for the A automaton to make a transition from 2 back to 1. And that means that the first automaton goes from 2 to 1, while the second automaton still stay in state 2 after the transition, after the C transition. And that means that if the A automaton is in state 1 and the B automaton is in state 2, nothing more can happen, because the only thing B can do is this small b event, and the only thing A can do is the A event in its current state 1 and in the current state for B state 2. So this is a terminal state, but it's not a marked state. So that means that it's a bad deadlock state. And in that sense, you could say that this is a very unsatisfactory situation. So we must avoid such states. And this could just be that we have missed some modeling aspects in our system. So one has to be careful with the alphabet of the set of events when you synchronize systems. I hope that you will see some, at least say one more example on this this afternoon in your tutorial. At least you can easily find such examples in the exercise session, in the exercise material. Okay, yeah. Actually, I planned not to say much more today. Let me see if I should go on with a little more. Maybe it sounds strange because we started a bit late, but we can see here. I can go on with something more. Yeah, I will add something also here on Patreon, not on Patreon because that's that takes more time. But let me see here if I can. Sorry, now I have missed something here. Where am I? I have too many windows open. There you are. So what I will do now is at least to illustrate some typical behaviors which you can model by automata and also by Patreon nets. And actually, I can describe also without making now the formal definition of Patreon nets, but I can explain that and coming back to the more formal definition on that later. So first, a very typical behavior which we have for this type of system is straight sequences. So for instance, if you have here an AI automaton, then you can make a transition with an AI. Let's say that we say A1 here for simplicity. So I equal 1. So in your A1 automaton, you can make a A1 followed by B1. And in a Patreon net, you have the same type of structure, but the transition is then labeled a little bit different with this vertical line here between one place and the next place. But in this case, with the event A1, you move the token from the first to the second place. And when the event B1 happens, you move the token to
the slide some.
Slide is not there.
Sorry?
The exact slide is not there. You are showing some other slide.
It doesn't work, so I have to start again. Can you see it now?
Yes, now it is correct.
Yeah, okay. Sorry. So this was a straight sequence. And you in the automaton, you move from the first to the second to the third state. And in the same way for the PetriNet, you can move a token from the first place to the second place to the third place. And you see that the events of this, you can use the same type of event names. In the PetriNet, you also have this, in this case, extra vertical line representing the transitions. Another important feature is that you can have alternative sequence or alternative choices. So for instance, when you are in the initial state here, you can make either an A1 or an A2 event. And if you take an A1, you will also follow up with B1. And if you take A2, you will follow up by B2. And in the PetriNet, this is modeled in rather the same way, because the token can take this way via the event A1, and then you have the token here and followed by B1, and then you get the token into this last place. Or if the event A2 happens, you take this direction instead, going via A2 to this place and then B2 to the final place. Now it's interesting that if you have these two automata, A1 and A2, which we had here, say that now your I is equal 1 and 2. So A1 means that you have the events A1, B1, and with the automata A2, you have events A2 and B2. If you take the synchronous composition of those two automata, what do you get then? You get this actually cross product of the states. So here you have the initial state in both. Here you make the first transition in the first automata, while the second automata is still in its initial state. Here you go to the final state in the first automaton via the event B1, and then you move with the second state into its second automata, to the second and third state. And this is one way to reach the final state. But as you see, there are other options. For instance, that you start with A2 to make one first transition, and then you can make the first transition in the first automaton A1, and then, for instance, continue with the second transition in A2, and then the second transition in the first automaton. So you see that this synchronous composition represents all possible ways for these two automata to reach the final state. And why you get all this combination is simply because there are no shared events, there are no shared behavior. They can work independently of each other. And that formalism is also called sometimes interleaving, if you have heard that. I will not talk very much about that, but that's a common notion in you could say formal models and also in planning literature. Now it's interesting that if you use the PetriNet, you get a much more simple model in this case, because here you can take the token via the event A1 to this place, and then B1, and then you have one token down here. And that corresponds to this way moving A1, B1 in the automaton. And then we take the second automaton going with A2, B2, but in the PetriNet, you move the token from the first to the second to the final place. And there are, of course, other situations, other combinations like A1, A2, and then both tokens in the middle place, and then say B2 and B1, and finally you have actually two tokens in the final place here. So in this way, let's think about that you instead had not 2 automata of this type, but you have, say, 5 automata with just 3 states. And well, maybe that sounds very academic, but it's actually a very common model, because that could represent an operation which first is in its waiting states, and then you go to the second state when it's working, and then the third state is a completed state. So waiting for start, working, and then finally a completed operation. And if you have 5 such operations and they are working totally independently of each other, you get actually a 5-dimensional system. So you get 3 to the power of 5 states. Which, of course, I mean, that's not very much. I think it's 81 states in that case. But the interesting thing is that, I mean, it's quite huge state space still. But for the PetroNet, it's just that you add 3 more sequences of the same type here. So you get simply much more simple models or graphical descriptions of systems if you use the PetroNet. And in that case, you could say you get a more readable description, especially when you have this type of concurrency. I think I skipped this one. This is another quite important application, which actually I think we talked a little bit about that yesterday also. I mentioned about this zone as a mutual exclusion zone. So you could think about the zone modeled in this way by an automaton R, and then the 2 robots could be considered as B1 and B2. And first then the robots ask for permission, and then they can execute when the robot resource is ready. They can take it, and then they execute B1, the first, sorry, B1 was a robot, sorry, this was the mutual resource, which in our case, the application we had yesterday was that the resource was the shared zone. So R is now the shared zone. So B1, it means that the first robot is using the shared zone, and then with C1, it leaves that zone. And B2 could have the same procedure, and then you have instead the events B2 followed by C2. And in that way, that is only possible if the shared zone is not used by the first robot. So it's not possible for B1 and B2 to use this shared zone at the same time. So this is a classical mutual exclusion model. If you model this by a PetroNet, you get once again a bit more of a readable system. Here you have the sequences B1, B2, and here you have a robot with or the shared zone, which either can be used for this sequence or for that sequence. And if it's used for the second sequence, the first sequence has to wait for it to get free again. This is a bit more special situation, which I think I will skip. And then I will come back to this presentation next session. I'm sorry if I asked to leave you some minutes early today, because in half an hour I will start another lecture and I would like to get some lunch too. So if you have a quick question, I can take that now.
Or maybe we can request the participants to either ask those questions in the afternoon or tomorrow, because you have hardly any time.
Well, a quick question I can take now. Otherwise, you know, I'm not participating this afternoon, so then we can take the questions to me tomorrow. But if you have 1 or 2 questions now, it's fine.
Participants, one or two quick questions, yeah, if you have.
It does not look like that.